definition of acids and bases collectively. We've always said that anything that dissolves in water and gives up an H plus ion is an acid. In our new theory, the only thing that's different is we're going to start defining acids and bases as a system, which means that an acid that gives up a proton, gives up an H plus ion, is always going to have a base associated with it. And the base is going to be the thing that accepts that H plus ion. So a similar definition, for acids, it doesn't really make much change for us, but it's going to fundamentally change the way we think of bases. Now, the reason this is necessary is because we don't have to worry about this with our strong acids. HCl, HNO3, so hydrochloric acid, nitric acid, sulfuric acid, though only the first of those two hydrogens, hydrobromic acid, hydroiodic acid, perchloric acid, and chloric acid are all strong acids. And that doesn't necessarily mean that they are more acidic than other acids. It still depends on the concentration, right? So this doesn't mean strong the way we think of strong, like it will burn you. That's true if you have a high enough concentration, but it's not true in a low concentration. A low concentration of HCl isn't dangerous. A high concentration of HCl is dangerous. But strong just means that when they dissociate, in other words, when they give up their hydrogen, they give it up completely. It's not an equilibrium. It happens all the way. If you have 1,000 HCl molecules, all 1,000 of them will give up the H. If you have 1,000,000, all 1,000,000 of them will. If you have a mole of them, all 6.02 times 10 to the 23rd of them will. So we draw that with a single arrow. But we're going to introduce our new theory, what we call the Bronsted-Lowry theory of acids and bases. And we're going to say that nitric acid is the acid, because it's going to give up that hydrogen, but it's actually going to give it to something in our new system. And the thing it's going to give it to is the base, which in this case is just water. And these are all happening in aqueous solution, so we have functionally a limitless supply of water. There's lots of water around. But what's going to happen then is the NO3 will now be written as -1. And no, we're no longer going to write this just as being H+, because the reality is an H+ isn't going to float around for long at all, because it's going to find water. Water is polar, which means it has a negative side, and it's going to stick to it. And so in reality, you'll get that NO3- ion floating around, and then we get H3O+, which we call the hydronium ion, though to be honest, we mostly just say H3O+. But if you hear hydronium ion, that's what we're talking about there. When we get to equilibria, this becomes important because then on the other side, that H3O+, well, that is now perfectly ready to act as an acid. In the reverse reaction, the H3O+ can give up that H+, in which case it will just become water. And the A- is actually perfectly ready to take an H+, in which case it would just become the original acid again. So the acid, once it gives up its H+, is actually now ready to act as a base. And so we call that the conjugate base. Conjugate means like mated to or paired with or tied to. So this is the base that is sort of mated to the acid. It's actually the same compound, it's just lost its hydrogen. And then the water turns into hydronium, and we call that its conjugate acid. It's the same compound, but now because it has a hydrogen, it can act as an acid and give it up. Does that make sense? And we have to think about it that way because both reactions happen. So HA will act as an acid, but then A- will act as a base in the other direction. And then H2O acts as a base, but H3O+ will act as an acid in the other direction. These will go back and forth. And eventually, if you leave them sitting, they will reach a state of equilibrium. Now, with acids, we said you can do the exact same equilibrium thing we've always done. Concentrations of the products on top and concentrations of the reactants on the bottom. But there's one thing that we decide to get rid of, because one of the things that ends up going on the bottom is the concentration of water. And the concentration of water in water, you can work it out. You could say 1 liter of water is in every 1 liter of water. That's not a very exciting statement, but it's true, right? And then we can say 1 liter of water weighs 1 kilogram of water. And then you could say 1 kilogram of water weighs 1,000 grams. And then you could say 1 mole of water weighs, what is it now? 18.02, right? And you could work it out. You can actually work out the concentration of water in water. And what you end up with is 1,000 divided by 18.02, 55.49. So the concentration of water is 55 moles per liter in water. In other words, it's a really huge number, which means if we react a little bit of a way, is that number going to meaningfully change? No, it never meaningfully changes. So that number is basically a constant. So rather than have to work with it all the time, what we do is we fold it into the constant, and we make a new constant that we call Ka. And in that one, for acid reactions, and only for acid reactions, we allow ourselves to just ignore the concentration of water, fold it into Ka, and be done with it. Does that feel okay? That feels all right? All right, cool. So now we can just do questions like we've done. A quick reminder, we used to say that pH was the negative log of H plus ions. In our Bronsted-Lowry theory, instead we're going to say pH is the negative log of the concentration of H3O plus. But that's functionally the same thing. Those are the H plus ions that got released. For a strong acid, we can just take the concentration of the acid, plug it in for that, and do, because all of the acid will turn into H3O plus. But for a weak acid, we have to work with the equilibrium. Now the good news is, you'll never have to find Ka. And the reason you'll never have to find Ka is every acid is very well studied. I guess if you discovered a new acid, like some organic acid, you would have to go in the lab and figure out its Ka value, which would be easy enough to do. Some years I've done that as a lab. We find the Ka of citric acid. This year, being 7 days behind, guess what we're not doing? That, it really bums me out how many labs we're missing because we've lost so many days to scorekeeping and tournaments and seminars and Brock. The trips are fine. I don't mind missing a day to a trip. I don't like missing a day for a sports tournament, which should be after school, and I don't like missing a day for like a university seminar when I'm trying to get you to university and have you do really well. You know what I mean? But I know I hate it. Like, but what you do normally with sports is you don't play all your games in one day. Every week you have a game for the whole season. Way nicer. Think how nice that would be, because after every game you get to go, first of all, every game goes to 5 sets instead, best of 5 instead of best of 3, way better. 25, 25, 25, 25, 15 on the last. And then secondly, after every game you get to go, okay, what went well there? What do we need to work on? Oh, it's so much better. I hate this model. I hate it. But it's what it is. I don't control it. You know what? Weird thing, they don't ask me what I think. Isn't that weird? Not weird? And when I offer my opinion, they say things like, that's good, Joe. And then they just keep doing what they're doing. Almost like they don't respect my opinion. Anyway, that can't be it. Let's move on. And fair enough, I don't even respect my opinion. So we looked yesterday and we said, okay, we can do this. We set up our ICE table just like the other Equilibria, where we put each chemical species up top. Why didn't I put a fourth one here for water? Because we folded that into our constant, right? So we're not going to need it. And then we put our initial conditions, and then we say how they're going to change. We come up with the final. We plug that into the equilibrium expression. We solve for x. We go back, use x to find the concentrations of everything. And then finally, if it asks the pH, not just the concentration, we can just take the negative log of the concentration of H3O plus, and now we have the pH. Boom. Cool. Good. Yes? All right. Now, this first one I gave you, we did, and we had to do a quadratic. You guys did a really good job. Good job remembering it. It's been a long time since we've done some of that grade 10, grade 11 math, maybe for some of you. So good job. But now we're going to do it again, but I'm going to give you a chance to make things easier. Assumptions make things easier sometimes. Now, can everyone put their pencil down? Because I don't want you to actually do this, but I want you to take a look at something. Is that fair? Can we look at the previous question? I'll even do it here. But look at the previous question. Our expression ended up being this thing equals x times x over 0.025 minus x. Does that make sense? That was our equation. And we had to do a quadratic because we had x squareds here, but then we had an x here as well. So we can't just take the square root. It's a complex trinomial, so we had to do the quadratic equation, right? But hear me out. I want to pause. I'm going to make a copy of this. I just want to show you something, and then we'll show you why that's useful. We did all this jazz, and we ended up with x being equal to 0.023. Okay, let's take a look. But I want to make a note here. The fact that x ended up equaling 0.023 means that this number here ends up being 0.025 minus 0.0023, and it ends up basically being 0.023. Does that make sense? That's the math we got. Well, you know what 0.023 is really close to? 0.025. So what if x had even been smaller? But even here we say, okay, what if we treated 0.025 minus x as equaling basically 0.025, i.e. not going to change much. Again, don't write any of this because we're going to actually do the example in the next one. I just want to show you where this comes from. Well, then I could have said 1.8 times 10 to the negative 4 equals x squared over 0.025. Then what could I have done? I could have just multiplied this side by, I guess if I wanted to be miserable, but I was thinking I'd multiply it by 0.025, multiply this side by 0.025, right? Can somebody do that for me? Get your calculator. You're going to need a calculator for every second of this unit. A quarter of 18 divided by 4 is, one second, I can do this, is 4.25. So this is going to be 4.25 times 10 to the negative, oh God, I can do this, I can do this, negative 5, negative 6, negative 6. Oh, damn it, right, okay, right, I knew that, I'm sorry, okay, there we go. And then, how would I solve this? I take the square root of this side, I take the square root of that side. Can you do that for me? I would get 2.12 times 10 to the negative 3, right? In other words, 0.0021. Okay, now, that is really close, but not close enough, right? So for the previous question, if I'd made that assumption, if I'd said, oh, that 0.025, it's not going to change much, and can I get your full attention, dude? You're going to need to do that. Put that right away. Give me, I promise. This you're going to need to know. If this had been just a little, if this number had been a little bit smaller, my assumption would have been true. So here's the rule then. We're going to come over here and we're going to say, when we get the concentration of HA minus X in the ICE table, we can check to see if it will likely change. And here's the question. Sorry, can I? Well, whatever. Okay, I did that stupid place, but that's okay. Here's what we do. It's an easy test. We say, I want to make sure I don't get this backwards. Ready? I'm just going to quickly check my filled in one, because sometimes I like to say it backwards, and then I get mad. Okay. Here's the test. Ready? We do concentration of HA divided by Ka. All right? And if that is greater than 500, then for 2 sig figs, concentration of HA minus X can just be treated as equaling the concentration of HA. That's the test. We test if the concentration we're given is at least 500 times bigger than the Ka it's later going to be divided by. In other words, if the Ka is only going to change this a small bit, then we can, for the purpose of our math, treat HA minus X as just HA. In other words, so little will be dissolved, so little will be dissociated that that won't meaningfully change, and that's going to make our math way easier. If you wanted to do it for 3 sig figs, you'd have to have it be bigger than 5,000. If you wanted to do it for 4 sig figs, it would have to be bigger than, yeah. So let me show you what that looks like in action so it's a little less confusing. Is that fair? Yes, it's a good safe bet, and I'll show you why. And to be clear, this assumption doesn't have to be, it's not true. We're making this is something we do in physics and chemistry all the time, where we say this won't be mathematically perfectly true, but because we're working with sig figs, it will be true to the number of sig figs we're working with, which means we can do that assumption and save ourselves some math. This is something you'd never be allowed to do in a math class because you're explicitly doing something that isn't mathematically true, but you can do it in a science class because you're doing it with the knowledge that it won't change your final answer. Does that make sense? It's a cheat. We call it an assumption or a test, but really it's a cheat, but it's one that saves a lot of time. So let's try this question. We have HPO4 and HPO4 2 minus and H2PO4. Calculate the pH, the concentration of H2PO4 minus, and the concentration of HPO4 2 minus of a 3.5 mole per liter aqueous solution of phosphoric acid. Okay, this question's a beast. All right, this question's an absolute beast. Ready? Before you write anything, H3PO4, when it acts as an acid with water, what's the reaction going to be? H2PO4, what charge will that have? Nope, it's giving up an H+, so it will be, and then what will the other thing be? H3O. Okay. And then that has a Ka value, and it tells us over here what it is, so that's okay. Now, reaction 2, though, because, ready, this is brutal, what can this act as? It can act as a base and go backwards, but it also is, in its own right, an acid. This is brutal, right? And what will it become? HPO4 negative 2. People were asking for this yesterday, by the way. They were saying, well, what if it's more than one acid? We're going to show you how. It's not that bad. All right? Now, that, of course, can go in reverse, so this will be an acid-base equilibrium. It has its own Ka value, but it gets worse because, what about the third one? This can also be, it still has another hydrogen, so it can react with water. And what will it form? PO4, negative 3, and H3O+. Now, here's the good news. Anytime you have a polyprotic acid, this is going to happen lots. In fact, we could check to see if it's one of our strong acids. It's not. So it's not going to happen completely. But if you look, we can probably find Ka values for it. They're not on that chart, so I must have given them to you in the question. And I did. Does that make sense? Now, we're not even going to, this is going to happen lots. This is going to happen a little bit. And this one here is going to happen barely at all. Does that make sense? In fact, we're not even going to bother doing any math for this one. Does that make sense? It just doesn't happen to an appreciable degree. So we're going to ignore it. Does that make sense? Whenever you have an acid that can give up more than one hydrogen, it gives up the first one pretty easily. It will give up the second one a whole lot less easily. And if it does have a third one, it'll barely give it up at all. Does that make sense? But I'm still going to show you how to do this. Our assumption that we just talked about is going to make life a little easier to do this. So let's give this a try. We're going to do this first reaction, which is H3PO4 will react with water. H3PO4, of course, in this case is the acid. I should write that below, not above. I'm going to regret writing it above. and water is the base. And they're going to form an equilibrium. And on the other side, we'll have H2PO4. It's given up an H minus or an H plus. That's what acids do. And the water will have to accept that because that's what bases do. So it will be H3O plus. We would now call this the conjugate. Nope, we'd call this the conjugate acid because it can now act as an acid. And we'd call this the conjugate base because it can act as a base. That's our first reaction. All right. And we're told that our concentration of the acid is what? H3PO4. The concentration is given to us in the question as 3.5 molar. Okay. And then the concentration of H2PO4 minus before anything happens will be 0. And the concentration of H3O plus before anything happens should be 0. Okay. Now, first just give me signs. Which of these are going up and which are going down? What's going to get used up? What's going to get made? Yeah, the acid's going to get used up, and the conjugate base and the conjugate acid are going to get made. And then the nice thing with acids and bases, at least, is if you look at the stoichiometry here, it is 1 to 1 to 1. Which means at equilibrium, what will this concentration be? It'll be 3.5 minus whatever x is. What will the concentration of this be at equilibrium? And what will the concentration of that be at equilibrium? Okay, so now if we go to write a Ka statement, Ka equals what in this case of this first reaction? 7.0 times 10 to the negative 3. Sorry? Yep, but this was acid 1, the first hydrogen, and this says acid 2. Does that make sense? So it's saying the first hydrogen of H3PO4. It could also have called this a H2PO4 minus, but here, and if you write it that way, that's totally fine. But here it's just saying the second hydrogen of H3PO4 minus, which is more often actually in a table. They'll just list H3PO4 and then show its 3 Ka values, A1, A2, A3. But either way you do it is fine. The first one is 7.0 times 10 to the negative 3, and that will equal what in this equation? At equilibrium, concentration of H2PO4 minus times the concentration of H3O plus divided by the concentration of H3PO4. And then we can say, okay, 7.0 times 10 to the negative 3, I'm going to zoom in, will equal, we can actually put numbers in here, or variables or whatever. At equilibrium, what will the concentration of H2PO4 be? X. What will the concentration of H3O plus be? X. What will the concentration of H3PO4 be? Well, it'll be 3.5 minus X. But now I want you to look. This equilibrium constant is a pretty small number, right? So it's telling us that not much of this is going to dissolve. We can do our check for down here. And quickly I go over here and I say, let's just check. Does 3.5 minus X equal 3.5 to 2 sig figs? And again, what do we do to check? We divide the concentration of the acid by the Ka, and we see if it's greater than 500. And if that's true, then we're good to go. What's the concentration of the acid to start with in this case? 3.5, and we're dividing it by 7.0 times 10 to the negative 3. That's going to be what? It's going to be 5 perfectly, which is nice. It's 500? Exactly. And I should have put an or equal here because we're going to call that okay. So this just passes. All right, and what that means is when we go to do the math down here, I don't have to say 3.5 minus x. I can just say 3.5. I'm going to put that star on it. You go, girl. And then what goes in here? What did we say the concentration of X and X? Very good. Oh, I used the wrong color. That's going to be silly of me. Sorry about that. I'm sorry, team. I failed you. I used all the wrong. I literally could not have done that worse if I'd tried. That was the worst possible job to do this. So now, what can we do with that 3.5? We can multiply this side by 3.5, right? Those will cancel. And we can multiply this side by 3.5. What's that give us in the next one? 3 times 7 is 2.1. 2.1 times 10 to the negative 2. And then half of that again is going to be 2.45 times 10 to the negative 2. How'd I do? 0.0225. Yep. The old boy still got it. And what's that equal? Hey, Novak, what's that equal? Just the 3.5 canceled, so what's left over here? Very good. X squared. Sam, how would you solve this? Beautiful. Exactly right. We can just take the square root of both sides. We'll take the square root of that side, take the square root of this side, and when we do that, we should end up with, I wish I'd left you guys a bit more room. I pulled such a math teacher thing here. Do you ever find that math teachers don't give you nearly enough room to do work? And then I've been told that I give way too much, but I figure way too much, all you have is some wasted paper, but not enough and you're confused. This is a math teacher note. That's not enough space. Anyway, we get an X that's equal to what? 0.16. Okay. Bless you. Now, to be clear, that is going to change 3.5. It's going to change 3.5 actually to 3.3. But if you go through and do this math again with 3.5 replaced as 3.3, you'll find that to 2 sig figs, you actually get the same answer. Just barely. So you get away with it. Does that make sense? We used to cheat here. And again, would a math teacher ever let you do this? No. This is a physics, chemistry, engineering thing. But now we can come in here and say that this ends up equaling 3.5 minus 0.16. And that equals what? 3.3. Good. What does this end up equaling? 0.16. And this ends up equaling 0.16. Okay, now, if this were a regular acid, we'd be done the question. We could just take the pH. But this isn't a regular acid. Our acid has a second hydrogen, right? Our acid can do a second reaction, where that H2PO4 minus can act as the acid. It can react with water, and what will it give us on the other side? HPO4 with what charge? HPO4 negative 2, and more H3O plus. So we have to watch out here, because we can actually end up with more H3O plus. Now, this is going to give us a little bit of interesting math, because now we have to put these in. We have the concentration of H2PO4 minus. We have the concentration. We don't need to do water, right? Because that gets baked into our Ka. But we do have to do HPO4 2 minus, or minus 2. And H3O plus. But now, look at the initial conditions. What's the initial concentration of H2PO4 minus? 0.16. Okay, now ready for this? What's the initial concentration of H2PO4? HPO4 negative 2 rather. 0, right? We haven't made any yet. But, Rutro, what's the initial concentration of H3O plus? 0.16. Does that make sense? We have some H3O plus to start with this time, yeah.
How come, the more you take away the hydrogen ion and the acid, the less it wants to give away its hydrogen?
This is actually going to tell you a couple of reasons why. One is to do with the acid itself, which is the first hydrogen that's going to come off by definition is going to be the easiest one to come off, right? Just makes sense, right? If you go to pick an apple off the tree, the first one you pick is going to be the easiest one, which means by definition, the second apple you go to pick isn't going to be as easy to pick as the first one. And the third one's going to be, so it's just, the reason is because if the second one were easier to pick off, it wouldn't be the second one to get picked off, it would be the first one. So that's the first reason, is that they come in order of easiness because nature is lazy and easy things happen before hard things happen. Low energy solutions happen before high energy solutions. Does that make sense? Which is a great question, by the way. So the Ka value is going to get lower and lower with each hydrogen because as we go, it's going to be the hydrogens that are more packed onto the thing and harder to find that happen. Or in the case of this, which is a simple oxyacid, there's now more electronegative, like there's now the same amount of negative charge on the anion, but only 2 positive charges, so they're held more tightly. But regardless, it's easier to pull a hydrogen away when there's 3 there than when there's only 2 there in this particular molecule. But then it gets harder for a second reason, which is the first time our concentration of product starts off at 0, which means that initial reaction is going to start off going pretty fast until it reaches equilibrium. But the second time around, the initial concentration of H3O plus the initial concentration of one of our products isn't 0. One of our products has a concentration as big as our reactant. Now, the other product has a concentration of 0, so this is still going to start going forward, but it's going to slow down way quicker. So it's a double whammy. The Ka is going to be lower, but then the other thing is it's going to slow down fast. Much faster than the first one slowed down because the first one started with no product. This is starting with as much product as reactant. You don't have to know that, but it's actually helpful to understand that. So did that make some kind of sense? Did I answer your question?
Does it also matter about like the concentration of water since like the water is kind of getting used up?
The concentration of water we treat as constant, and it functionally is constant. You weren't here when we did at the beginning. We actually worked out the concentration of water, and it's like 55.3 molar. So if that goes down by 0.16, it's still functionally 55 molar. It's not meaningfully changing. Did that answer your question? These are good questions. Now, and it actually changes less than that for a different reason, but don't worry about that for now. We'll get that in a later lesson. Now let's do the thing we always do. Which of these is going down, which is going up? This will go down, this will go up, this will go up. And because it's a nice, easy 1-to-1 to 1-to-1 reaction, they'll all just go by X. Good. Now, that means that we can write what these will look like at equilibrium. At equilibrium, what will H2PO4's concentration be? 0.16 minus X. What will HPO4 2 minus's concentration be? And what will H3O pluses be? 0.16 plus X. Okay, now, here's the good news. We can do our little test again. All right? We can check to see if, for math purposes, 0.16 minus X is going to basically equal 0.16. All right. And what's our check again? We do the concentration divided by the K value, and it's got to be greater than or equal to 500. 500 is just pushing it. You just get away with 500. Bigger is better. So let's do our check. What is the concentration that we're starting with? 0.16. And then look up at the question. What's the K value here? Might as well write it here while we're at it. Ka2 equals times 10, negative 8. All right, that is a really small number. Is that number, when we divide 0.16 by it, do we get a number bigger than 500? I think we're going to get a number much bigger than 500. It's 2.5, well, let's just write it. It's 2,500. Oh, wow. Is that bigger than 500? True. Which means, therefore, we can actually get away with both these. 0.16 plus or minus X will just equal 0.16 when we go to 2 sig figs. Does that make sense? This one, the last one, was a bit of a sketchy. It was just at the limit, we might have done ourselves a favor by actually doing a quadratic. This one, there's absolutely no point in doing a quadratic because those values are going to not meaningfully change, which makes sense because we said that second acid barely dissociates, right? Yep.
So for both of the concentrations, you would just use 0.16, like either it's
Yep.
negative X or positive.
Very good. So let's write this out first just with what goes on top, what goes on the bottom, not the numbers, but the actual thing. What goes on the top of our Ka law of mass action? Yeah, the conjugate base. So in this case, the HPO4 negative 2, and the conjugate acid, which is always H3O plus. Good. And what goes on the bottom? Very good, which was, even though it looks like a conjugate base, this is our acid in this case, right? And we can keep in mind, again, we don't have to put water down there because water is baked into Ka. So 6.3 times 10 to the negative 8 is equal to, and now we can actually put numbers here, but again, we can use our assumptions. What's the concentration of HPO4 2 minus at equilibrium? Nope, HPO4 2 minus. X, right? Products go on top, right? But then what's the concentration of H3O plus at equilibrium? We can just treat that as 0.16, right? We don't have to worry about it being okay. And what about the concentration of H2PO4 minus? 0.16. All right. Which, if you look here, those are just going to cancel. So we get really easy math here. What does X end up equaling? Now, let's really quickly ask ourselves, in this case, does that change this at all? Okay. Does it change this at all? 0.16 plus X would be 0.16 plus 0.1234567763, which would equal 0.1600000063, which to 2 sig figs is 0.16. So that really didn't change, right? So this will just equal 0.16. The reason I don't have you bother to work with the third hydrogen here is, did the second hydrogen change the pH of this solution at all? It went from the first hydrogen leaving phosphoric acid got us to a concentration of 0.16. And when all the second ones that leave are going to leave, the concentration is still 0.16. So do you see how there's no point in checking if the even weaker third hydrogen is going to make any change? We could stop now. If we wanted to, we could check the third one, but it's got to be weaker than the second one. And if the second one isn't strong enough to change the pH, then the third one definitely isn't going to be. Does that make sense? Now, having said that, what is the concentration of HPO4 2 minus here? Okay, so let's actually answer the question, because the question given is, what is the concentration of, calculate the pH. So what is the pH then? pH is the negative log of the concentration of H3O plus ions present. And in this case, that means taking the negative log of 0.16. 0.1 would be a pH of 1. This is a bit bigger than that. So this is going to be a pH of 0. But not much. I'm going to say 0.8, give or take. 795. Yeah, listen, the old guy. Even a broken clock team, right, twice a day. 0.796? 795. So that'll be 0.80. I had a high school physics teacher who would always do logs in his head, and unlike me, he'd get them right every time. I get them kind of sort of right once in a rare while, but he would like consistently get first digit and usually a decimal of logs like just straight off his head. And we'd always be like, how do you do that? And Chop would be like, it's kind of intuitively obvious, don't you think? And I'd get so offended. I'd be like, it is really not intuitively obvious.
And how do you get it?
Having done it, so not because it's intuitively obvious, because I've worked with it a lot. Hey, those of you who had me for 3U Math, can I ask a serious question just before we move on? There's potentially a second 3U Math class opening up next semester. Am I serving students well if I sign up and say, hey, I want to teach that rather than getting a supply teacher in? Like, was I okay at that? I'm not looking for a compliment here. I'm looking for serious feedback.
No, it was good.
Worth doing? Okay. All right. I think I'm going to throw my hat in the ring and see if they'll take me.
I think you should, because like we were like a bad group to have.
You were not a bad group. You were a lovely group, but you were a...
Unfocused.
You were an unfocused group.
But I think even if your group...
You think push through a bit harder?
Yeah.
Push through and get to everything?
You did miss a few things,
Okay.
which isn't too much of a problem.
So do it again, but be less kind?
Yes.
Got it. Okay, sold. So therefore, we can say, therefore, the pH of the... What was the original concentration? 3.5 molar? 3.5 molar H3PO4 is 0.80. And I want to make a note here, so when you look back at this, since the second hydrogen didn't change the concentration of H3O+, there's no reason to evaluate the third one. Now, if you really want to know what the concentration of PO4 minus ions with no H at all was, then you could go ahead and do that. But spoiler alert, at these low concentrations, it's just going to be the Ka value. You're going to get that same thing where things cancel out. Yeah.
Like the second hydrogen did not change any of the concentrations. Would it be the same for every acid, or
Not necessarily, but usually. It is very rare to have an acid where by the third hydrogen it's releasing it very much. Because even look at the first one. To be clear, the first one, it took 3.5 molar H3PO4 to get a measly 0.16 molar H3O+. That is a really low percentage, right? Like you can do the math right there, but what's 0.16 out of 3.5? And that's going to be like 5%, right? Give or take? Yeah, so 4.5%, right? So even if you take a super concentrated phosphoric acid, and this is by no means a super low Ka value, Ka values get way lower than 7.0 times 10 to the negative 3, only 4.5% of that is turning into actual H3O+. Weak acids mostly don't dissociate. So by the time you get to a weak acid's third hydrogen, and there's some that have 5 hydrogens to give up, it's not meaningfully making any difference. Does that make sense? Which is also why, like in theory, don't write this, okay? Don't write this. But just so you know, like in theory, if you have, let's say, something like this, what compound is this? Propanoic acid. Good. Okay. You could look up the Ka for this. We could look up the Ka for propanoic acid. And like, I don't know. Let's look it up. Propanoic acid Ka value. And we got Libratex. And we look up propanoic acid. Okay. And we get a Ka value of 1.34 times 10 to the negative 5. That is already a low Ka value. Does that make sense? 1.34 times 10 to the negative 5. That is 100 times lower than the one we just did, right? So you're talking, this is going to be a really weak acid. This is not going to be the kind of acid that is like burning through things and destroying metals. Does that make sense? Organic acids are used for all kinds of things, but they're not used to like break down things hardcore because they're just not good at that. They're weak acids. In theory, this hydrogen has a Ka value too. It could give up this hydrogen. It could. But the Ka value on this would be like whatever times 10 to the negative 100. You know what I mean? In theory, that hydrogen could fall off and this thing could act as an acid there. In theory, methane could act as an acid and one of those hydrogens could get off. It's just that the odds of that happening are going to be like so low that functionally it doesn't really happen. Does that make sense? Like one of the things to start to learn in the universe is that we live in a probabilistic universe, which means that really nothing's impossible. Anything could happen. And like, that's not just stupid, like university student, like getting high with his friends for the first time being like, man, anything is possible. Like, it really is. Like, anything is possible. Like, but some things are so improbable that they never happen. But that's not the same thing as being impossible. And in chemistry, that's definitely true. Anything that can happen in chemistry will happen, but some things happen so infrequently that you don't ever have to worry about them happening. They don't matter in the actual doing of chemistry. Was that useful, or did that just go way overboard and make it more confusing? Sunana, did that answer your question at all? Actually, or are you just shutting me up now? A little bit of both? Okay, I can live with that. Okay, this is about as bad as a question can get, where to figure out the pH of an acid, you had to test not just one of its equilibria, but actually two of them. I really can't make an acid equilibrium question much nastier than that, you know? But there's one other thing we want to look at. Ready? There's one other thing we want to look at, which is, we said there's water everywhere, right? Water everywhere. And here's where we get into a little bit of trouble. What if water didn't bump into phosphoric acid? What if water didn't bump into nitric acid? What if water didn't bump into hydrochloric acid? What if it bumped into another water? Could one of these choose to act as an acid, and could the other choose to act as a base? I can't see any reason why not. What does an acid do? It gives away an H+. So what's that going to become on the other side if it gives away an H+? It's going to become an OH negative. And what about this one? If it's acting as a base, we already know what water acting as a base becomes. H3O+. And that, of course, is your conjugate acid. Now, this should start to show you why the Arrhenius theory, the new theory we have of acids and bases, and the old theory we have of acids and bases, which is, which was the old one's the Arrhenius theory, the new one's Bronsted-Lowry, because what ends up getting released here by the base? I don't like my colors here. Oh, I do like my colors. What I do, guys, what I do.
For the previous example, you wrote H2 as conjugate base. And
Did I get backwards?
as conjugate acid.
Say it to me again. Where did I do that?
Right there.
Here? Yep, H3O plus is the conjugate acid. Because in the reverse reaction, what does it do? In the reverse reaction, it gives up a hydrogen. And in the reverse reaction, what does this do? In the reverse reaction, it takes the hydrogen. So in the reverse reaction, it acts as the base. Did that answer your question? That last one's a bad example to look at to think of that, because this H2PO4 can actually act as a base and an acid, because it can do the reverse reaction by accepting an H+, and it can also do its own forward reaction and act as an acid. So that's a terrible way to learn that concept, because it's a tricky one. So much better to look at, look here, much better to look at a simple one like HNO3. Well, that's a strong acid. Like HCO3. No, that's H2CO3. Like HClO2 is a much better example. Because here, obviously, which one of these is an acid? Which one's going to be the base? That's the acid. And obviously, this is going to be the base. Now, when HClO2 acts as an acid, what does it do? It gives away that hydrogen, which means it becomes ClO2 with a negative charge. And the H2O, which has accepted that, becomes H3O with a positive charge. Now, keep in mind, in the reverse reaction, they can go like this, which means in the reverse reaction, H3O is the acid. Good, which would mean ClO2 minus, because in the reverse reaction it takes an H, would be the conjugate base. That takes a bit of practice to get used to. All right, you're going to screw that one up. Yes?
You might have already answered the question, but in the before and then number 5, how can water be
Because much as we say it's reacting with itself, it's really, here's a water, here's, I actually have two of the same remote. So this is, here's a water, here's another water. When they bump into each other, they can do different things, right? This one can give something away, which means it's going to act like an acid. And this one could take it, which means it's going to behave like a base. So it's because you physically have two waters. It's not actually itself. We pejoratively say itself because we're talking about two waters, but really it's this water is going to act as an acid. It's going to give something away. And this acid is going to act like a base and take it. Did that answer your question? It was a good question.
Okay, part two. So like, this just sounds really stupid. I've put water from one glass to another glass. How does OH and H3O get made?
So every glass of water you've ever drank has OH minus in it already and H3O plus in it already. Every glass of water you've ever drank is actually full of a little bit of the ion that we say makes something an acid and a little bit of the ion of something that we say makes it a base. Now you're going to discover not much. Water isn't a very good acid, and it also isn't a very good base. So it does this, but it doesn't do it very much. But it has a Ka value just like anything else. Does that make sense? Now, because water is going to get folded into this twice, we don't call it Ka, we give it a different name. But look here, if we were going to write an equilibrium expression for this, we'd say Keq equals, and what would go on the top of this? Concentration of OH minus times concentration of H3O plus divided by the concentration of water times the concentration of water. Okay, now, these, again, are going to be basically constant. Why did I write this up here when I made a space for it? Guys, why did I write that up there when I made a space for it? I made this note. You know who made this note? I have no one to blame. I made it. Okay, so let's try it here. The Keq for this would be the concentration of OH minus times the concentration of H3O plus, and that'd be divided by the concentration of water, and then times the concentration of water again. Well, is there any reason to include these two things, which are functionally constants? They are not going to change. And if they're not going to significantly change, if we did that with the one concentration of water when we did a normal acid reaction, when we're using water as an acid, we can do it with both of those. And so we get something, we don't want to call it Ka, because Ka only folds water in once. So we're going to call this Kw. It's a special case. This is the dissociation constant of water. Basically, it's saying this is the constant for how often water breaks into these things. And the answer is not very much, but you're going to find this number to be really noteworthy. It is 1.00 times 10 to the negative, and this might start to make sense of a scale that was always a little bit screwball-y, 14. What scale related to acids and bases had this weird thing that happened? Huh? The pH scale. Yeah. So if you look here, neutral water, really quickly. Neutral water. If we make an ICE table for it, this is going to be a really boring ICE table because it's just going to be the concentration of OH minus and the concentration of H plus, right? H3O plus. And initially, those are both 0, right? Because before the water acts as an acid and base, there isn't any. Are these getting made or used up? Made, so they're both plus. You look at the reaction, what's the number on them both? This is an acid base, so it's going to be 1 to 1 to 1, simple stoichiometry. So we can just say plus X and plus X. So at equilibrium, the concentration of both these will be X, okay? Now, that means that 1.0 times 10 to the negative 14 equals X times X. 1.0 times 10 to the negative 14, equals X squared. So how would we solve for X? We take the square root of both sides. And that means that if we take an X, what's the square root of 1 times 10 to the negative 14? Well, obviously it's 1 times 10 to the negative 7. So the reason neutral water has a pH of 7 is because 1.0 times 10 to the negative 7 is the concentration of both OH minus and H3O plus in neutral water. And let's quickly calculate the pH of that. It would be the negative log of 1.0 times 10 to the negative 7, which would be 7. So that's why the pH of neutral water is 7.
You have the thing for the pH too.
Sorry? Say it again.
To find the concentration.
Above, like the above equation about how like water turning into OH
Mhm.
minus and H2O plus.
Yep.
Is that why you told me that when I drank distilled water, it would like taste more acidic?
No, actually, because this will be both acidic and basic. Now, the truth is, it actually will make it just a little bit. It'll make it a little bit acidic. So it would actually, you can never have water. There's no such thing as water that isn't a little bit acidic. But this is such a small number that's functionally meaningless. It's also a little bit basic, which tastes a little bitter. But again, it's so small, it's functionally nothing. No, the reason distilled water actually tastes more acidic than regular water is related to acid-base equilibria, though. It's that carbon dioxide and water form H2CO3, which is carbonic acid. H2CO3 acts with water as an acid, and it would give us, of course, HCO3 minus and H3O plus, right? So CO2 gets into the water from where? From the air. So water that has stuff dissolved in it normally won't dissolve much CO2 because water can only hold so much stuff. So if it's got minerals and stuff like that. But when we do our next lesson, we can actually figure out how much CO2 water can dissolve if it's got nothing else in it. And you'll find it's a pretty high number. So it can dissolve a bunch of CO2. That will form H2CO3. And some of that H2CO3 will form HCO3 minus and H3O plus, which means that if you leave water sitting out with nothing in it, it will slowly become acidic if it's in an environment with carbon dioxide in it. And so by the time you taste it, it'll have a little bit of a sour taste to it, and it has a bit of acidity. Whereas if you left salt water out, because it's already got a bunch of stuff dissolved in it, it's not going to dissolve much in the way else, and it will, not be as acidic. You don't need to. Nobody needs to know that. That was a tangent. I want to get through this question, so I'm going to have you put a pin in that so we get through this. Okay, now listen. Using this information, we can always find the concentration of OH minus in water given the H plus or reverse. Here's a rule to know. Remember that Kw is equal to the concentration of H3O plus times the concentration of OH minus. And that always equals 1.00 times 10 to the negative 14 at standard temperature and pressure. By the way, K values change in different conditions. So now, let's say, for example, that we know that we're given the concentration of OH minus is equal to what in this case? 6.8 times 10 to the negative 5? Well, if we know the OH concentration, then we can figure out the H3O plus concentration. These things always live in a balance. If you make something more acidic, if you put more H3O plus into the solution, what has to go down for this still to be true? if you add H3O plus, like we have been in the last bunch of reactions, what must be happening to the concentration of OH minus? This always has to stay constant. When you multiply them, they have to give you 1 times 10 to the negative 14. So if this one gets big, this one has to get small. On the other hand, if we give you a base, if we make this one big, then this one has to get small. They have to move together. So if we know that the concentration of OH minus is 6.8 times 10 to the negative 5, let's find the concentration of H3O plus. Well, that's easy. The concentration of OH minus times the concentration of H3O plus always equals what? 1.00 times 10 to the negative 14. Well, that means that 6.8 times 10 to the negative 5, the concentration of the shampoo we were given, times the concentration of H3O plus, has to equal 1.00 times 10 to the negative 14. So all I have to do to solve for the concentration of H3O plus is divide this side by 6.8 times 10 to the negative 5. And of course, what I do to one side of an equation, I got to do to the other. And that's going to give me a concentration of H3O plus that is equal to what? Somebody do that math? I mean, it's going to be on the order of negative 10. 10 divided by 6. It's going to be 1 point something times 10 to the negative 10. 1.47? Cool. Okay, now, really quickly, let's find the pH, and it asks for the pOH. pH is equal to the negative log of the concentration of?
But the concentration of H3O and H would be the same thing? Because it says the combined concentration of the H and...
Oh, yeah. Sorry, we will use these interchangeably. Concentration of H plus and concentration of H3O plus are synonyms in chemistry. All right, they mean the same thing. Okay, so can we find the pH of that? It's the negative log of the concentration of H3O plus. And what will that be? The negative log of 1.47 times 10 to the negative 10. And that is going to be 1 times 10 to the negative 10 would be 10. This is a little bit bigger than that. So it's going to be 9.3? 9.83. Okay, I was way off. Way off. All right. pH is 9.83. Okay, what about the pOH? We haven't done that in a while, but if pH is negative log of the concentration of H plus, this is the negative log of the concentration of OH minus. And we already know the concentration of OH minus. That was in the question, right? Which is what? 6.8 times 10 to the negative 5. And that is going to be 4.2-ish. Oh, it's definitely going to be 4.2. Check it.
4.17.
Perfect. Okay. And I knew that. How did I know that? Am I just super smart?
You didn't say 4.17.
I said 4.2, which 4.17 is 4.2. So there's another way to know that, which is if you do a little bit of fancy math with this equation, if you know your logarithmic rules, you could actually develop this yourself. But we can just see it right here. What do you notice about these two numbers? Note, this can be a really helpful trick. pH plus pOH always equals 14. This is always true.
Always. Every time.
At standard temperature and pressure. So again, K values always change at different temperatures, but this is always true at standard atmospheric temperature and pressure.
Is there like a...
Because the dissociation constant of water just so happens to be 1.00 times 10 to the negative 14. The really crazy thing is, that is not, like that just happens to work out to a round number. It's just one of these rare things in life that just gives us a nice number. Like that didn't have to, that could have been 3, like most of these things aren't nice, right? Like most of your K values aren't nice. Most of your, and it just happens that the one we use the most often is a nice round number. Now, we picked a temperature where it ends up being a nice round number. If you did it at like, 30 degrees Celsius, it'd be like 1.25 times. You know what I mean? So we kind of cheated by picking a temperature where it works nicely, but still pretty cool, eh? Okay, is there homework on this? Oh, shoot. I meant to give you homework. That's okay. I'll give you homework tomorrow, I guess. On Monday, I guess. I might post some practice to teams that you can do if you want. That would be helpful. You want to keep up on this stuff. Or if you have the textbook I gave you, I'll post some questions for there as well. I can't stress enough, this unit's going to come like a freight train, so getting your practice in is going to be really helpful. Really, really, really helpful. I'm not trying to scare you, except I'm totally trying to scare you. Work hard in this unit, all right? This unit's going to feel a little bit like, we're going to go from maybe 60% of the pace of university up to this unit. We're probably going 85-90% of the pace of what it really feels to be like in university, all right? We're going fast. We're still not going as fast as university does, but we're going pretty darn close, all right? Push hard. Do well. You're all more than capable.